doesn't matter. It doesn't even bother to check. It just drops it. So the same, you can do a number of different things with the DCRPC calls to do evasions. So like I said before, you can fragment your DCRPC requests. So you can send 1 byte in time inside of your actual call. So you would say, I want to call function 1, and you really want to send 1,000 bytes of data. You can send them 1 byte at a time and do 1,000 actual DCP calls, but only be 1 call request. You can also do something. You can also encrypt your requests. Supposedly, Dave Attell has released encryption for his DCRPC implementation. I haven't actually seen it yet.
It's actually, the encryption mechanism is already part of the in-packet library released by Core SDI. So if you go to like corest.com and click on like the open source link, you can find a DCRPC implementation that already uses the crypto stuff and packet privacy stuff. So if you're worried about people not implementing this in their exploits, all the major exploit engines will have it really soon, if not now.
Yeah. And then one of the other things you can do is, so in your request, you're sending what's called a stub. So the structure that you're sending across the wire. You can append a lot of junk data in it. And each of the different, in a number of the different fields, they have my data is actually at the offset of 4. So in between where your actual value is, for where my data is and your actual data, you can pad that with a number of with junk. And then at the end of your DCRPC request, you can append as much data as you want, and the DCRPC engine will just ignore it. Your IDS might not. And then one of the other things that you can do is you can also Microsoft added something they called an object ID. So normally what you do is you bind to a handle, you take your handle, and you do a call on that handle. Well, they added what was called an object ID. You could say, instead of calling to this handle, I want to actually do this call on this specific object, and it's a UUID that's sent across the wire. Normally the way it happens is that object ID is the UUID of the service that you're talking with. Well, in all the services that are implemented today on Microsoft except at Exchange, that object ID, even if it's provided, is ignored. So you can pad out another 16 bytes in the packet of random crap, or something that you actually wanted to, to make the IDS say, hey, this is not an exploit, even though it might be.
A side side effect of the NDR stub and being able to append data to the end of it is that NDR, anything you put into the stub is calculated as part of the length field of the DCRPC call, even if the program you're talking to doesn't decode that part of the stub. Where that matters is if you're doing an exploit for DCRPC service and you want to stick some shellcode into it, but you don't really have enough room for your shellcode, just stick 4 megabytes of shellcode at the end of your DCRPC request and it works fine. Just put it on the end of your regular stub data. It gets sent across the wire. It's usually pretty close to your regular stub, and just tell it to jump 1,000 bytes forward, and you're going to land right in your NOP slide and the rest of your shellcode. So it's a really easy way to basically put unlimited shellcode into any DCRPC exploit just by appending it to the end of the NDR stub data that's never decoded by the application. So,
oh, and if your IDS requires you have the whole DCRPC request before you can process it, not only do you have to track all of that, you also have to track it inside of SMB, and then inside of TCP, and then inside of IP, all of which can have fragmentation.
Fragment, segmentation, out of order, everything. So it's a fun times.
It's a nightmare. And then the other thing, like I said, DCRPC has a number of different transports. You can do RPC over HTTP via proxying. Like I said, you can take an RPC request over IIS has a feature where you can proxy DCRPC to a DCRPC server. Normally it's implemented as locally, so you can expose DCRPC services via the web. Well, you can also expose RPC services inside of your network, so simple proxy servers. If this is all done via using the UDP version, but you can also do this over the UDP version of DCRPC, which is a DCRPC version 4, but you implement it over TCP over HTTP.
If anyone remembers the old messenger overflow, the UDP-based one that Shock and I'm spacing the name. Basically, there's this great demo of a UDP-based exploit that was demonstrated at CanSec West a couple years ago. Oded Horowitz. They did the demonstration on that. Basically, they had a single UDP packet that would trigger a heap overwrite that they did one at a time over and over again. And the way that Microsoft fixed the vulnerability is by basically disabling the entire UDP interface for that service. That was just one service out there. There probably are, the overflow occurred when it processed UDP requests and not when it processed TCP requests. So there may be other services out there that only bind to UDP that you can also find vulnerabilities in just by attacking the UDP interface only. But kind of a side thing, sorry. So the way that, if you have a name pipe and you're trying to bind to it, like let's say you're trying to talk to a DCRPC service, that service is part of a certain process. That process has a name pipe, and you can talk to that name pipe via SMB. That's the normal kind of chain from getting to a certain process on a system through SMB from the outside world. So you connect to SMB, you authenticate, you open a handle to the name pipe, then you bind to the UID of the service you want inside that process, and then you talk to do your requests. In the Windows world, a lot of services actually share the same process, and they share the same process and they share the same name pipes inside. And the way that the RPC implementation works in Windows is any one of those name pipes that are part of that service, if you can bind to any of those pipes anonymously, you can attack any one of the services that are part of that process, regardless of they're part of the same service internally. Kind of convoluted, but basically, if a good example is the browser pipe. The browser pipe is part of the browser service. The browser service runs in process with 5 or 6 other services, a lot of which have had vulnerabilities that have been discovered in the last couple of years. You can exploit nearly all of those DCRPC attacks by first binding to the browser request and not binding to the browser pipe, not to the pipe that you normally would, like NT services or workstation, and then actually getting to the service through that other mechanism, through a different service in the same process. So if you expose any pipe that has anonymous access inside the process, and you've got other threads in that process that also do RPC calls and expose the interface to it, all of those interfaces are not exposed to anonymous users as long as there's one way for an anonymous user to access that process. So kind of a bad description, but.
All right, so one of the things we were talking about is for how do you handle strings. So let's show you how NDR handles encoding an ASCII string. So the way it works is you send a length so first you have to set the type of numbers you're sending. So is it big endian or little endian? Normally it's sent in little endian. So you set I'm sending 5 bytes. Then you send your offset to your data. Most of the time it's sent as 0, but you can also increase your offset and add in additional junk. And then you send your total length of your data. So if you have an offset, you increment that as well. And then you null pad your data to the 32-bit boundary because NDR is designed to be more portable. And then you're supposed to use nulls for the rest of your padding. Well, one of the interesting things, a number of IDS is still currently broken for, is they look for nulls for the padding. You don't have to use nulls. You can just use random junk. The actual end host will say, I'm supposed to read 5 bytes, and then the rest of it is just junk and ignore it. So one of the other things that's interesting, a couple of different issues is how you handle sending the empty string. So if you're going to send a null. So normally the way you would think it would work is you send a length of 0, then say the offset of 0, and the total length, well, the 0, and then the string of 0. Well, if your string is nothing, then to pad it out to the 32-bit boundary, you need 4 bytes of null. Well, a number of the services implement sending null strings this way. Well, a number of other services in DCRPC land will just send 4 bytes of null, saying, hey, my length is 0, and just skip it. So you have to know which version of the middle compiler they used to know how they're marshaling a null string, because most services you're not actually going to expect seeing a null. So the developers never hit the differences between the different middle compilers. So one of the great things out there in DCRPC land, for a long time, IDS developers didn't really understand how NDR or DCRPC worked. So a great example of that was when Blaster came out. How many remember reading the Blaster exploit? Okay, so like 10 of us. It was really awful. It was a great big massive chunk of hex, and then a bunch of guys, their exploit, what they did is they just changed they changed all the lengths in the blob of hex when they inserted their overflow. They went back and fixed all of the offsets inside of the packet. Well, so one of the things that IDS developers did. So how do they look for this? Well, the Blaster was using using a DCOM request. Well, so one of the things they did is each of the different objects that are sent via DCOM is marshaled via a meow prefix for each of the objects. So all the IDS vendors said, hey, wait a minute, we're not supposed to see DCOM. Let's look for the meow string. Well, if you actually look at the actual implementation, the meow string is just there for padding. You don't actually have to say meow. So the DCRPC implementation that's in Metasploit just sends random junk for this. So the great thing, the actual vulnerability was in an overflow in a path. So what you do is you look for // and then a really long name and then a slash. That's, the actual end vulnerability was that. Well, the great part was there are 8 objects in the request. The 7th one is the bad one. Well, the 7th one happened to be processed first. So in the previous 6 objects that were sent, there was a large amount of extra data that you could add. If your IDS was a first pass out, so if you saw a directory and the first directory that it saw was too short and it dropped the packet, you could evade the IDS. Evaded a lot of IDSs at the time. It still evades a couple IDSs as today. So the great part. And then a number of the different objects had strings that had an unlimited size. So you could send over a meg of data in a specific object and push out push the IDS into a state where it has to track way too much data, and most IDSs at the time would just drop the request. And again, because it was the vulnerability, like we said, was for paths, for an overlong path, all the different path vulnerabilities applied. So the Unicode vulnerabilities we're going to talk about in a little bit, the adding the // and then the triple slashes and all that other stuff, all of the IDS, those all had to be taken into account as well before the overflow happened. So the IDS had to take care of all that as well. So all right, so we're going to go into some additional protocols, some text protocols. So one of the things that's interesting is that what's called header folding. So a number of the protocols out there today, HTTP, SMTP, iCal, actually emails themselves have what's called header folding. So if that header line is going to extend beyond what should fit in a normal terminal, the developers, what they're supposed to do is break it up into multiple lines. Well, a number of different applications handle how they break apart the lines and how they put them back together differently. There's a couple of broken email clients that send what's supposed to be the header, evil header, and then what you see on the screen, the bar biz foo. What they're supposed to see is that. Well, you can send a couple of the different email clients actually send the same, to send that. They break it across and make it look like what's on the bottom. So if you note, the first one is totally broken. There's no Z in the biz. So there's a number of different implementations of clients and the resulting servers that just handle the header folding just wrong, and how they reassemble those back together. So how do you know what your application does? Well, you have to test each and every version and how they handle them, and including how they handle new lines and spaces inside of the header folding. I guess we're going to go ahead and talk about some client-side attacks. A large number of vulnerabilities that are coming out these days, thanks to HD and the browser of the month, browser bug of
month of browser bugs, I guess, was the name of the topic. So the name of the blog.
There are a bazillion bugs in web browsers and local mail clients and MP3 players and whatnot. So how do you handle this? How do you make your IDS handle that? How do you handle each of the different versions of IE and all the vulnerabilities? Well, there's no real firewall. There's so many ways to do lots of different evil things. We're going to talk about a number of the evasions that really most of the IDSs can't have, have no way to solve these problems. So the first one is Unicode. So HTTP, you can Unicode encode all of the data that's sent over HTTP. So all of the HTML exploits that HD released last month. So you can encode them. There's a number of different UTF encodings. So UTF-16, both in Big Endian and Little Endian, and UTF-32 again in Little Endian and Big Endian. And there's also a couple others, UTF-7, UTF-8. We'll talk about those in a minute. Normally the way you do it is you send a header with a content type, HTML, and then a char set. Which character set are you going to use? Which version of Unicode are you going to use? Well, the great part is a couple of different browsers, not all of them support if the first 2 bytes in the packet are an invalid character set. So FEFF will say it'll force it to use, say, the rest of this document is now UTF-16 Big Endian. And so without sending the content type, you can force, the browser will know, hey, process the rest of this request as UTF-16 Big Endian. A number of the IDSs don't handle that yet. All right, we'll talk about UTF-8. So UTF-8 has a number of different evasions that you can do inside of that. So there's a large number of ways that you can encode the letter A. So normally you would encode it, you can just say A. You can also hex encode it of 41 with an